Swati Ghadge, Assistant Professor, Department of Civil Engineering from Walchand Institute of Technology, Solapur. Topic for today's session, Analysis of Simple Truss by Graphical Method. At the end of this session, learner will be able to analyze simple truss by graphical method. Simple truss means two ends of the truss are simply supported. It is shown in the figure. The joint method, section method, moment method and the graphical method are the methods by which we can analyze the truss. In this session, we are learning graphical method. Graphical analysis was developed by force polygon drawn to a scale for each joint, and then the forces in each member were measured from one of these force polygon. The number of lines which have to be drawn can be greatly reduced, however, if the various force polygon are superimposed. The resulting diagram of the truss is known as Maxwell's diagram. These are the steps which have to follow to draw the Maxwell's diagram. It is also called as vector diagram or the force diagram. Take one numerical. The simple truss shown here. At joint A, there is a hinge support. At joint B, there is a roller support. And two external forces are acting at point C. So, first step is draw support reaction by using equilibrium equation. So, at support hinge, there are two unknowns, VA vertical and HA horizontal. And at roller support, there is only one vertical, VB, perpendicular to support. These are the support reaction. VA is minus 14.5 kilonewton, VB is minus 5.5 kilonewton and HA is 12 kilonewton. Here minus sign is indicating the assumed direction is wrong. Means VA and VB are acting vertically downward and HA assumed direction is correct. Now to draw vector diagram, give name to the space that is called as Bose notation. So in between space VA and VB is space A, this is space B, this is space C, this is space D, and between 12 kilonewton and VB, the complete space is space E. The member CD is also divide space in two parts, so we will give name to that space, that is space F and space G. So this is what space diagram. Now this is space diagram. We will draw the vector diagram. For that, take a suitable scale. For the explanation point of view, I have taken a simple scale. 1 centimeter is equal to 10 kilonewton. You take a suitable scale, that how much big or how much small diagram you want. Accordingly, you vary the scale. Now we will move in clockwise direction. So we will start from space A. So in between space A and B, there is a vertical downwards force VA. So VA is 14.5. So I will draw 1.45 centimeter line, which is indicating the 14.5 kilonewton as per the scale that we have taken. Then in between B and C, horizontal force is there of magnitude 12 kilonewton. So it is 1.2 centimeter line that we will draw while drawing the vector diagram. Then in between C and D, the 2 centimeter line we have to draw to indicate the 20 kilonewton force, which is vertically upward. So arrow is must because it is a vector diagram. Then from D and E, in between D and E, there is a horizontal force 12 kilonewton. So 1.2 centimeter line we have to draw, and it is a cross check. Then it is between E and A, there is a vertically downward force of magnitude equal to VB. So it is 5.5 kilonewton. So the external equilibrium of the truss that we have completed. Now we will find out the remaining spaces, that is G and F, to find out the magnitude of the forces. So in between A and G, there is a horizontal member AD. So I'll draw a horizontal line, and on that line anywhere G may be. Now from C to G I have to show one force, which is the force in member AC. So I will draw a parallel line to AC from space C. So it is a parallel line, suppose, and this intersection point is C. So to systematic representation, I will just erase it. So this is the intersection point, that is G. Then G to F is there's a vertical member, and E to F there is a member CB. So I will draw parallel line from space E to CB. So CB parallel line I will draw here, and it is coinciding with point G itself. So G and F are the same point, it indicating that the member CD is of zero member force. So there is no force in member CD. So this is what a Maxwell diagram or a vector diagram. Now this is a vector diagram and this is a space diagram. So simply by measuring the length from the vector diagram, determine the magnitude of all the members and complete the table. That table is indicating magnitude as well as nature. But how to determine the nature? Let us see. So to find out the nature of member AC, take joint A for the analysis. Consider the equilibrium of joint A. So for that you just check the space A, B, C and G are the surrounding space to joint A. You just identify here A, B, C and G. So you can see this diagram, you just make it separate. So this is the separate diagram and it is indicating the equilibrium of joint A. So one direction is known to us, that is A to B. Now it will move B to C, then C to G and then G to A. So these are the direction of other member. Now you copy that direction to near joint A. So here I just copy this direction, and the opposite direction you show to the another end of the member. See here I have shown that direction near to joint C, and opposite direction here I will show near to joint D. Now it is indicating that member AC is in tension and member AD is in compression. So right here AC is in tension, T stand for tension, and AD it is in compression, so it is C. Now just take one more joint for the analysis, say joint B. So A, E and F are the surrounding spaces of joint B. You just simply identify these spaces in the vector diagram. A, E and F, that small triangle. Okay. So it is here, and one direction is known to you, that is from E to A. So remaining direction you show here, because as it is in equilibrium, so remaining direction is also in same direction. So all the forces are moving in same direction. Now you copy that direction near to joint B. So see, this is same direction I have shown here, it is near to joint B. So opposite direction I will show near to joint D. Now I will copy this direction, it is near to joint B, and opposite direction I will show near to joint C. So CB member is in tension and BD member is in compression. So like this you can complete the equilibrium of joint and find out the nature of all the members. This is the answer diagram. See, member CD is of zero force. Now answer the question. Select the correct equilibrium diagram for joint C from figure number 2. So this is joint C. You can see here the surroundings spaces of joint C is C, D, E, F and G. C, D, E, F and G. Now C, D, E, F and G. So which is the correct option? So option C is the correct option. This figure is indicating the equilibrium of joint C. This is my reference for this video. Thank you very much for the watching.